So just now we had written frequency response function h of omega in its polar form as mod h of omega into e raised to j phi of omega. And later on we had derived this expression for h of omega in its real and imaginary part. So you can now see that this is a polar form, this is the rectangular form. We all know that when you want to relate polar form in the rectangular form, the magnitude of the rectangular form is nothing but under root hr square omega plus hi square omega, and face of the rectangular representation will be tan inverse of imaginary part, which is hi omega, upon the real part, which is hr omega. So this is what we get. This is the final expression for the magnitude function and the phase function. Now here, if I want to specifically define hr of omega, then hr of omega will be nothing but summation h of n into cos omega n. This is what we had replaced in terms of hr of omega, and hi of omega was nothing but minus summation h of n into sine of omega n. Now if you observe carefully, if I replace omega with minus omega in hr of omega, then the only term with omega is cos omega. If I replace omega with minus omega, cos of minus omega n will be nothing but cos omega n. That is because cos minus theta is exactly same as cos theta. So hr of minus omega will be same as hr of omega, and that means this is nothing but an even function. And if I do something similar for hi of omega, if I replace omega with minus omega, then I get sine of minus omega n. Sine of minus theta is equal to minus sine theta, so that minus sign comes out, and hence hi of minus omega will be minus of hi omega, and that makes it an odd function. Now what does that mean? That simply means that hr of omega is an even function, hi of omega is an odd function. And because of that, if you observe mod h of omega, hr omega, hi omega, because they are in the squared form. So now if I replace omega with minus omega, and if you take square of both, this will be exactly same, and this minus sign will also become plus due to the square. So that further means that mod of h of omega, that means magnitude function, is also the even function. And if I consider phase function here, if I take tan inverse of hi of minus omega upon hr of minus omega, hr of minus omega is same as hr omega, hi of minus omega will be minus hi omega, and tan inverse of minus theta, that minus will come out, so it's minus tan inverse of the same thing, and that makes phase part as odd function. Now if that is the case, what is the final conclusion? The final conclusion is that because the range of omega that we have taken is from minus pi to plus pi, what do you mean by even and odd function? The fact that mod h of omega is even function and phi of omega is an odd function, all we should know is mod h of omega and phi of omega for the range of omega from 0 to pi. That's it. If I know these two functions from 0 to pi, then I also know these two functions from minus pi to 0. That's because of this even and odd symmetry that we have. For example, if I tell you that some signal is even signal, and if I draw its right hand side part, because the signal is even, you can also draw its left hand side part, it will be exactly same. And hence all we should be interested in both the function from 0 to pi. This is even symmetry. If there's a symmetry in the opposite quadrant, it is called odd symmetry. So let us take up one numerical on this. We will be given some system in its difference equation form, transfer function form, or impulse response form. We will be asked to draw the magnitude response and the phase response. What we have just now discussed is few important things about frequency response of the system and the nature of magnitude and phase functions. But please remember that this symmetry is valid only when h of n is real signal, which is the case for all the practical systems.